So in this video, we will derive the expressions that can be solved for the due temperature, due pressure, bubble temperature, and bubble pressure for an ideal mixture of n components that follows Raoult's law. Now, Raoult's law we actually have not talked about yet, but basically what it states is that the mole fraction of some component in the liquid phase times the pure saturation vapor pressure of that component is equal to the mole fraction of that component in the vapor phase times that total pressure. So there are a few more things that we are going to need before we can derive expressions for all these things here. So the first thing that is going to help us get the due temperature and bubble temperature is going to be the Antoine equation, which I've pulled up right here. So I'm just going to write that down on the board here. So Antoine equation and for our purposes, it's going to be log base 10 of the pure saturation vapor pressure. And then that will equal our A minus B over C plus D. And then one more thing that is actually going to be useful for us for calculating the bubble pressure is I'm going to make this little diagram. So we're going to have a container of 30% benzene and 70% toluene. And it will have a piston on top. Like so. And it will be given to us at 323 degrees Kelvin. So the first of these that we are going to go after is going to be our bubble pressure, which is the pressure at which the first bubble of gas is formed at a certain temperature for a liquid mixture. So in order to get an equation for this, we're going to go back to this diagram. And one thing that I forgot to mention is that the outside atmospheric pressure is obviously 1 atm. So from this diagram, we already technically have our mole fractions of our components, since this will all be liquid on here because of the piston. So, and we also know the temperature, 323 degrees Kelvin. And from Raoult's law, this side of the equation of just the mole fraction times the total pressure, this is actually just the partial pressure of the component. So using that on this, we can get our equation for our bubble pressure. And it's just going to equal the sum of our partial pressures. So the sum of our partial pressures. And then again, as I just said, the partial pressure is just equal to the right-hand side of this equation. So that means that we can substitute in the left-hand side for this partial pressure. So it'll be the sum of mole fraction times the pure saturation vapor pressure. And this is the mole fraction in the liquid phase. So now we have an equation for our bubble pressure. So now we are going to find the expression for the equation of bubble temperature. And bubble temperature obviously is a lot like bubble pressure, but instead of the pressure at which the first bubble of gas forms at a certain temperature, instead it's the first bubble of gas formed at a given pressure, and it's the temperature at which that happens. So for our expression for the equation of the bubble temperature is going to be a lot like our equation for the bubble pressure. So I'm just going to copy that down. But instead of trying to solve for the pressure, we're trying to solve for temperature, obviously. So this is where the Antoine equation comes into play here. So we can just substitute that in to our bubble pressure equation. So instead we'll have 10 to the A minus B over C plus T. And obviously you could solve this equation for T, but obviously since we're using Python, it's so much easier to just not do all that algebra and just have an expression with T in it, and then worry about that when we get to Python. So now we will be going for our expression for due pressure. And due pressure will be the pressure at which the first drop of liquid is formed at a certain temperature for a mixture of gases. So we're going to come back to this diagram here. But instead of being at 323 Kelvin, it's going to be at 400. So that our mixture is gases instead of liquids. So in order to find that due pressure, what we would be doing is compressing this until we got our first drop of liquid. So what's that going to look like for our equation? So our due pressure equation. We're going to start off with Raoult's law, but we're going to solve it for our mole fraction in the liquid phase. So what that would be is, it would just be Xi equals YIP over our pure saturation vapor pressure. Like that. And one thing that we need to remember is that our mole fraction here of Xi is going to be equal to 1, obviously, because the 2 added up is going to be 1. That seems very obvious, but it is very important. So we can set that equal to 1. And then to our other side of our equation. And to make that equal to 1, it will be the sum of these mole fractions and the sum of this. So now we just need to kind of figure out what we know and what we are looking for. So we are going to know this mole fraction of the gases from our container here. And we can also calculate the pure saturation vapor pressure from the Antoine equation using the temperature that we are given. So what we are trying to find is this P up here, so we can bring that out in front. So it'll be P times the sum of this mole fraction over the pure saturation vapor pressure. And now finally, we can divide both sides in order to isolate this P. So our final equation will just be that P will be equal to 1 over our sum of Yi over our pure saturation vapor pressure. And that will be our equation for the dew pressure. So now finally we will get our equation for our bubble, or for our dew temperature, the same way that we got it for our bubble temperature. So we're just going to be taking our dew pressure equation and we will be substituting in the Antoine equation with our T in it for our pressure here. So this will be the sum Yi over, and it will be 10 to the A minus B over C plus T. So now we have derived expressions for our dew temperature, dew pressure, bubble temperature, and bubble pressure.